Hello again. I'm in some cramped quarters today, as you can see, for the pre-lab for Density Calculations Part 2 as part of the York College of Pennsylvania General Chemistry 1 curriculum. I'm in my office today as opposed to the lab where I'll normally be for pre-labs to show you how we're going to use a spreadsheet to analyze the data that you collected in the first part of the experiment, which you should have already completed by this point. So to begin today, I'm just going to open up an Excel spreadsheet, and as I do that, I'll zoom in on the screen and you'll be able to see my computer screen the rest of the pre-lab, and hopefully my voice will carry over so that you can understand the commands that I'm doing. But I really want you to be zoomed in. So while Excel loads up, it's already done on my computer. It might take a little bit longer on yours. Let me move in as close as I can get here and get you focused on it. There. Okay. Might not be able to see, but I'll certainly go through the audio commands that I'm using to let you know what's happening here. I'll also try to increase the size of my screen so that maybe it's a little bit better for you to visualize what's happening here. Okay. Now I won't analyze the data that you've necessarily collected, but I want to show you how to type in formulas and equations which can allow you to quickly calculate a number of results as opposed to having to use your calculator by hand to calculate maybe 10 or 20 results like you might have in today's experiment. So let's say I was studying the area of a series of rectangles, and I had collected length data, so I've typed in length and width data. And I have a series of lengths that I've measured, let's say 10 centimeters, 15, 20, 25, 30. And that the widths of my objects were a variety of random widths. I'm just making these up now. How about 32, 17, 14, 12, and 10. And now I want to calculate the area. So rather than calculating each area by hand on my calculator, I'm going to use the spreadsheet to type in formula into this cell right here. Now all formulas begin with an equals sign. Excel will calculate a value if you simply type in the numbers, but if you want to tell it to do a formula, a repeatable formula, you begin with an equals. And I can either use the letter notation, so this length is in A2, so I could type it in. But as soon as I type it in, notice that it put a box around, hopefully you can see that in blue, around the length, the times symbol, and then B2, and it put a green box. Alternatively, I could have clicked on the cell B2, and again it highlighted that. When I hit return, it gives me the value. Now this wouldn't save us a lot of time if I had to type in equals A3 times B3. The real power in the repetition of the spreadsheet comes in the fill down feature. So I've clicked on my area box again. It shows my formula up here in the formula bar. Now I'm going to grab this corner. Please notice the mouse. The mouse does a bunch of different things in Excel. And now it's going to change to that a small crosshair, and when I grab it and pull it down, it repeats that formula for the respective cells across from the newly highlighted cell. Okay, so here I could see if I do click into C3, it took A3 times B3. So that is the area of each of these rectangles that I drew, okay, or considered. Okay? So that's a very simple formula. What if these were, instead of being widths, what if this was the radius of a circle? Okay, I'm going to delete out my area formula. Okay, and I wanted to find the area of a circle. Well, the area for a circle is pi times r squared. So I can type in pi. It recognizes pi as a built-in function or built-in feature of Excel times, again, this is my radius, and I want to square it. In Excel, the way to raise a number to an exponent is to use the caret symbol. So Shift 6 will give me the exponent 2. So that is going to square the 32 and then multiply it by pi. Now it says equals a name, and so I've made an error in my formula here. And let's see if I can figure out if this is a formatting issue. Sometimes it's how the cell is formatted as a number. Let's try that. Nope. So what's my area here? Maybe I'll put in some parentheses. Nope. So I've got a bit of a problem here. Okay. What if I put in 3.14159? Okay, it seems to like that, so it seems to not be liking my use of the pi for pi. I apologize. That was the first time I had tried that, but it looks like you can simply type in the numerical value 3.14159 times. The parentheses are not necessary, actually, the b squared. The parentheses would be necessary if this was, rather than the area, the diameter of my circle. If this was my diameter, I would need to divide it by 2, right? And I could do that in one formula rather than creating a bunch of formulas. I could still type equals 3.14159, my value of pi, times. Now I want to take my diameter divided by 2. So that's my radius in effect. And I want to square that. And like your calculator, the computer understands, the spreadsheet understands the order of operations. And so first it's going to complete the operation inside parentheses, divide the diameter by 2, and then it's going to square that and multiply by pi. And so then we see that the areas are quickly calculated, again using the fill down feature. The real nice feature is if I now collect some extra data, as soon as I put in another value here, it automatically updated it because it understood that I was doing this in a column. A series of data was being collected. So as part of today's exercise, you'll generate a variety of formulas to transfer your or translate your mass and volume values that you have into density values. And the density formula is, of course, mass divided by the volume. And so it will be pretty quick and easy. One other thing you might do is make a graph, or you will make a graph in today's lab. So let me briefly walk you through how to make a graph. I've highlighted the data that I'm going to use to make a graph, and I went up to the Insert menu, and I'm going to insert, here are a variety of charts. They're called charts in Excel, a graph, and we could use any number of possibilities. I'm going to use the scatter feature. This is popular in scientific work to show the relationship between two variables. And even among scatter, there are some options. We prefer if you use this first option where no lines are put in. Okay, we'll add trend lines later on. Okay, so it made it a rather large graph. I'm going to shrink that down a little bit. Okay, so now I've got the graph of area on the y-axis versus diameter. This was diameter on the x-axis. I could tell which one it put onto each axis because of the scale of the numbers. I know my diameters go from 8 to 32. and look at the size of these numbers here, and then my areas are much larger. The default when you highlighted values of data like this is that the first column will be used for the x values on your graph, and the second column will be used as the y values in your graph. So as a hint, you're going to make a graph of mass versus volume. So you'll want the volumes to be the first column that you highlight and the masses to be the second column that you highlight. Now we could add a trend line to this data. A trend line is a mathematically calculated line of best fit. So it shows the pattern in the data. In this case, you would highlight or click onto one of the data points and right-click the mouse. Not left-click, right-click, and some options show up. I hope these are showing up on the screen. Let me bring this up to where I know it's showing. Sorry if that wasn't. And so I've right-clicked again, and I'm going to add a trend line. And a series of options comes up on the screen for me to choose from. Normally we graph things so that we have a linear relationship. In this case, I know that this data, though, is a polynomial of second order, so I've chosen that. But let me try to force a straight line through it, and we'll see that it's not a very good fit. Oftentimes we like to add some features to our graph, to our lines, where we display the equation and r squared. R squared is a parameter or a property that tells us how good the data fit is. 1.00 is a perfect fit. Otherwise, anything that's imperfect will be less than 1, and the closer you are to 0, the worse the fit is. Okay? So for adding a straight line, I don't think I'll get a very good fit. Okay, and you can see here it gave me a 0.9769. It also added to my legend this. If we don't like these things, we can delete them, by the way, and it stretched out the graph. I always try to think about how it looks best. We're going to add titles, you'll add labels. Those can all be done using the chart tools options. You really just need to explore. And here are the layout options. There's a drop down of a bunch of options, and you can scroll through and decide what you would like. I clicked an option, and unfortunately it eliminated everything that I had. It's because it's trying to fit everything into this window. I can scale down my oops, accidentally tried to save there. I could scale down the size of everything. Please do take some time to consider how to make your figures and your graphs look good when you create them for your labs. You can even get rid of the lines. I just clicked on one of the lines and it highlighted all of them, and I can delete those lines. Alright, so remember my trend line was 0.9769 was the data fit when I used a linear. If I use a polynomial now, and I did not show the equation, now I got a perfect fit for this data. R squared equals 1, and here's the all-important function that gives me every point if I added additional points on this line right here. I'm going to delete the whole graph right now and get out of there. Okay. So again, you'll be guided through by your instructor today a number of the formulas and functions that you can use in Excel. I'm going to show you something as well today that will get you started towards next week. Let me open up Microsoft Word, and I'm going to complete the pre-lab questions for this week's lab in Word as opposed to writing them out. And I want to do this to show you how to start to use the equation editor feature that is available in Excel. In Word. I believe you could use it in Excel as well. So your first pre-lab question today asks you to find the density of an object when the mass of the object is 12 grams and the cube has a length of 35 millimeters. And we want the answer to be in the SI standard unit, which is kilograms per meter cubed. So the first thing I need to do is to calculate the volume of this cube. I'm going to insert an equation, and now a variety of options have popped up. Okay? And so I'm going to use some of the options on the right side of the screen. I hope they're still showing up for you there. Let me maybe scroll up there. Okay. I'm going to use the subscript and superscripts. In this case, I'm going to use a superscript. The volume of my cube, now I'll use the right arrow to get out of that, equals, okay, and the volume of any cube is equal to the edge raised to the third power. So I inserted a superscript, and again, to get out of the superscript, simply right arrow. So then that equals, I will insert a parentheses, although actually I'm going to insert another superscript, and in the box here, parentheses, all right, the length of the edge is 35 millimeters, and now I'm going to cube that. So that equals 42.9. Sorry, that is not right. 35 cubed. 42,875 millimeters cubed. Okay. So now I want to calculate the density. So our formula for density, I'm going to insert another equation. Density equals, I'm going to use the fraction bar this time. A variety of fractions. I'm just going to use the standard mass divided by volume. I'm going to continue to use the fraction bar. So the mass I had is 12 grams divided by my 42,875 millimeters cubed. I need to use that superscript again, millimeters cubed. So that would equal 0.000279 grams per millimeters cubed. But I need to convert this to the SI standard. So I'm going to use a unit conversion. So times symbol. This over here has all the variety of mathematical operations you could ever ask for. So to convert grams to kilograms, 1 kilogram is equal to 1,000 grams. So I've put kilogram over 1,000 grams. And then also times by. To convert millimeters cubed to meters cubed, well, let's put this whole conversion factor into parentheses, because we're going to have to cube the whole thing because it's a volume. So millimeters are in the bottom. 1,000 millimeters are equal to 1 meter. Right keystroking all the way to the end. So I'll take my answer, divided by 1,000 and times by 1,000 cubed, and I get 280 when I round for the significant figures now. Correct units of kilograms per meter cubed. That's the answer to pre-lab question 1 this week. Pre-lab question 2, what is the density of a solid object? 15 grams. And we've got the displaced volume. It displaces 11.6 centimeters cubed or milliliters of water. One of the nice features about this is I can simply copy a part of the previous one. So for number 2, and now I can paste this and simply change the values. And this is a powerful technique that you can use throughout the semester, because you will use some formulas again and again, and so you can go back to old lab reports and grab pieces of them to simply save you some time. Alright, so I had 15 grams divided by 11.6 centimeters cubed. Alright, and this time I'm going to have to convert again to my standard unit. So I'm going to copy the second portion, bring it down here, paste it in. Again, I'll be converting grams to kilograms, but I have to convert centimeters cubed. So 1 meter is only 100 centimeters. So I've got this all listed out as one calculation. 15 grams divided by 11.6 would be 1.29 grams per centimeter cubed, divided by 1,000 times 100 cubed this time is 1,200, oops, in the wrong spot, 1,293, but for the 3 significant figures, I'll have to round that to 1,290 kilograms per meter cubed. And that is my answer to pre-lab question 2. Number 3. Number 3 asks us to calculate an average and a percent error. So an average is obviously found simply by adding up the 3 values. I could insert a formula for you real quick if you'd like to see that. Average equals, here's a, we can do the sum of values divided by the number of values. So in this case, that would be 34.52 plus 34.50 plus 34.63 divided by 3 values. Our average is 34.55 milligrams with units then. To calculate a percent error, this is something we commonly calculate to see how accurate we are in our experimental work. The percent error formula is to take the absolute value, so that would be straight lines that I'm inserting, of the actual or the true value, goes by some different names, minus your experimental value, divide that by the actual or true value, and then to multiply that by 100% to put it on a percentage scale. Alright, so that equals, I'm going to drop down to another line, so that equals, for our problem, we're told that the actual value is 34.58 minus 34.55 divided by 34.58 multiplied by that 100% equals 0.087%. And there you have it. Now you'll learn, again, just like I mentioned with graphing, to make stuff look nice. Here the script is a little tight. The lines appear to be overlapping. That's because of the line spacing. So I'm going to right click on the and use the paragraph. You could also accomplish this from the upper menu. And I'm just going to increase the spacing maybe to 1.5 lines. And now it added a little more room, and it makes these formulas look a little bit nicer. Sometimes the numbers look a little small. You could increase the font size. There's a lot of things you can do to make your figures look nice in your lab reports. That's something you'll start to focus on next week. But here are the answers to this week's 3 pre-lab questions. The first 2 calculating densities, the next one calculating an average and a percent error. Again, I hope you'll learn a lot as you explore the functions of Excel. We like to use it a lot in chemistry to help us generate graphs and to calculate the results of a number of different experiments. And with that, I'll wish you a good lab. Enjoy.